Let's look at a position velocity equation. Let's try to find an equation for piston velocity. So a piston is inside of a cylinder, and that piston will go up and down inside that cylinder at a particular velocity at a particular RPM or RPS, revolutions per second or revolutions per minute, whichever way you want to use it. So if we look at this R, this is actually like the arm on the crankshaft that's spinning. So there's a little arm on there which is connected to the rod that holds the piston. This particular rod has a length, and this particular arm has a particular length to it as well. Probably the easiest way to try to find our distance from our pistons to the center of the crank is to divide this up into two triangles. This would be triangle 1, down here would be triangle 2. So let's look at the first triangle to try to find this particular distance from here to here. So our triangle is going to look similar to this. We know this side is L. Let's look at this side. This side, we can find this length over here by looking at this triangle down here by saying this would be the sine of theta is going to be opposite over hypotenuse. So we know that this is going to be R sine theta. Oops, sine theta. And then this side over here is just going to be Y. So if we use C squared is equal to A squared plus B squared, which is Pythagoras' theorem, we know that C is going to be L, so this is L squared is equal to Y squared plus R squared sine squared theta. Well, we want this in terms of Y because we're trying to find Y, so we're going to subtract Y from both sides. We're going to subtract L squared from both sides, so we're going to get negative Y squared is going to be equal to negative L squared plus R squared sine squared theta. Well, we got to get rid of the negative because that's not good. So we have Y squared is equal to L squared minus R squared sine squared theta. Well, we want to get rid of the square root, so we get Y is going to be equal to L squared minus R squared sine squared theta square root. Well, we've found the length from here to here. Let's find the length from here to the center of the crank. That will be relatively easy. This is going to be the adjacent side over the hypotenuse, which basically is going to be, we'll call this Y1, we'll call this Y2, is basically going to be R cosine theta. We take these two and add them up, we're going to get Y. So that Y is going to be equal to R cosine theta plus L squared minus R squared sine squared theta square root. This is our position vector. Basically the equation that's going to give us our position. So in order to find the speed, we're going to have to take the derivative of that with respect to time. All right, so let's do that. Now, when you take the derivative of this equation with respect to time, don't forget this equation is in terms of theta. So if it's in terms of theta, we got to use the chain rule, because the chain rule is going to tell us that you need to take the derivative of this thing as well as the derivative of the theta. All right, so dy dt is going to be equal to negative R sine theta minus, without doing the math, R squared cosine theta rather, sine theta divided by L squared minus R squared sine squared theta square root. And then the whole thing needs to be multiplied by d theta dt. Because you have a d theta here and you have a d theta on this side, you factor it out, d theta to t. Now don't forget, this is basically your RPM or RPS, revolutions per minute or revolutions per second, whatever the case may be. That's what this particular piece is right in this here. So that's basically our RPM times this thing. So this is the equation that's going to tell you the velocity of the piston. But there's an interesting little thing here. If you take this r out, this particular r, take one of these r's out, so you're going to have a dy dt is going to be equal to negative r sine theta minus, let's take that r out, so you have r cosine theta sine theta divided by L squared minus R squared sine squared theta square root. All right, because you're taking that R out, and then we're going to multiply this whole thing again by d theta dt. All right, this thing here is actually an interesting little equation. Let's look at this triangle again. So if we look at this triangle again, only this time we're going to look at this particular angle, and we're going to call it phi. So we know this side is L, right? We know this side is L squared minus R squared. Let me get a little bit more room in here. I need a bigger boat. Let's say that L squared minus R squared times sine squared theta square root and we know that this is R sine theta. So if we look at this triangle again, and if we take the tangent of this triangle, we're going to get the opposite over the adjacent. So tangent phi is going to be R sine theta divided by L squared minus R squared sine squared theta square root, right? This thing is actually this thing. All right, so in reality, let's look at our equation again. So in reality, dy dt is going to be equal to negative r sine theta minus r cosine theta tangent phi. And we take this whole thing and we multiply by d theta dt. And one more thing we can do. Let's factor out this r so that dy dt is equal to, we're going to factor out a negative r. And by the way, this is actually should be plus. I made a mistake right here. This actually should be plus. Let's factor out this r, so this would be negative r. I'm sorry, this is minus. I made a mistake. This is minus. Minus. Factor out our r, we get sine theta plus tan phi cosine theta rather, times d theta dt. This is our velocity of our piston. This is the piston velocity equation. So all you engine builders out there, you can use this equation to try to find your piston velocity. NASCAR engine builders probably use this as well. It is the best equation to find the velocity of your piston. Anyway, I hope it helps you. Please subscribe.